Our plan is to use the integral to find the electric field around a ring of charge. But before we do that, let's just pause and talk about symmetry for a little bit, because applying some concepts of symmetry to these problems can often simplify them a little bit, and we'll take advantage of symmetry as we go on throughout this course. So let's return to our point charges. We'll use what we did right here, then we'll apply that to our line of charge. And then we'll think about what is the electric field at point P. If you think you know the idea already, go ahead and hit pause and draw that electric field vector at point P, and then finish watching to make sure you got it right. Okay, so as a quickie recap, when we had our 7 charges, we drew the electric field vector due to charge 1. It pointed down and right. Then we drew the electric field vector due to Q7. That was the same distance from the middle, or from Q4, that Q1 was above it. And that electric field vector pointed up and right. Because Q1 and Q7 were equal distances from the middle, those electric field vectors had y components that canceled. So E1 and E7, the y's cancel. So with Q1 and Q7 being the same distance from Q4, means Q1 and Q7 are symmetric about Q4, or symmetric about the midpoint. Okay, the next two we dealt with was Q2. The electric field E2 pointed down and right. And Q6, again, those are symmetric around the middle point. That electric field pointed up and right. The y components canceled. E2 and E6. Y's cancel. Now that's just shorthand notation for saying the y component of electric field vectors 2 and 6 sum to be 0. All right, the next two are 3 and 5. Those are symmetric about charge 4. Electric field E3 points down and right, E5 points up and right. Those y's components cancel. E3 and E5, y's cancel. And then E4, which was right at the very middle, that didn't have a y component, it just pointed to the right. So E4y, that was 0 all along. So when we go to do our vector addition of our electric field, in this case of the 7 charges, we do the sum of all of our y components. That gives us our net y component. That's 0 because all of those y's canceled. Our x component is the sum of all the x components. That guy is not 0 because they all point right. They don't cancel. So then our net electric field vector was the x component in the x direction. And then we can draw that vector if we wish. It would point to the right. Okay, hopefully that makes sense. All right, let's take these ideas and apply them here to our long line of charge, or our continuous charge distribution. First, let's talk about the symmetry. So for our discrete charges, they were symmetric about the middle. That's true for our line of charge too. We want the electric field at point P. It's a distance from the middle, and our rod is symmetric about the middle. So let's draw a line representing that symmetry. Okay, so the rod is symmetric because half the line's above, half is below. Okay, so in our point charges, we picked Q1 and we drew E1. We picked Q7 and we drew E7 because Q1 and Q7 were symmetric. How does that apply here? Well, we don't have an individual charge, Qi. We have elements of charge, dq. So our first step is let's draw an element of charge. I'm going to draw it right at the top. It doesn't have to be at the top, but I'm going to pick it just because it's really easy to illustrate and make an analogy with Q1. So this is an element of charge at the top of the rod. It doesn't make what we call a discrete electric field. It makes an element of electric field. So this is just a difference in notation when we go to our distributions. That element of electric field, because our rod is positive, it points straight away. Okay, so this is similar. This dq is like this q1, except we're just talking about a small charge, so we call it dq. It makes a small field, so we call that dE. Okay, now to get the symmetry, we have to pick another dq that's symmetric with this guy. So if this dq is on the top, The other guy to look at is the one on the bottom. I always call it the twin or maybe the mirror image. So whichever spot you pick up here, you have to pick the symmetric spot from the lower half of the rod. So I'll pick the one right on the bottom. Let's ask what happens because of this DQ. So this makes an electric field at point P, which is going to point up and right, TE. Now have a look at these two electric field vectors. These are just like vectors 1 and 7. They point up and right, down and right. The up and down cancel and the rights add up. So we get exactly the same behavior. So let's write our result. So our net y part of the electric field, instead of saying the sum, we have to say the integral because the integral just means the sum of many small parts. And our x component is the sum of all of our x components is not 0. So our net electric field vector then will just be the x component in the x direction, and we can draw that electric field vector. Okay, hopefully that makes sense of an idea of symmetry. You pick two spots, equal distance from the point of symmetry. You look at your vectors after you draw them. You ask what cancels. So that's the whole idea of identifying the symmetry. You're asking the question, what cancels? Try and get through the next problems a little bit more quickly now. So what if we take our long positive rod and we form it into a circle? We make a ring of charge. What would the electric field at the center be? So let's start by identifying one tiny little bit of charge, dq. Let's draw the electric field that it makes at point P, dE. Now what we have to do is find its twin, its mirror image. So let's ask, what is this symmetric about? I would say it's symmetric about this line right here. So if this is the DQ that we have, and we want to find a place where we might see some cancellation, we have to pick the point exactly opposite on the circle. So we have to pick over here. So let's draw in the line of symmetry. So our circle is symmetric about that line. Let's pick our second DQ, which is going to be exactly opposite the first DQ because we're trying to see what cancels. Let's draw the DE made by that DQ. Okay, what we notice here is that they cancel. So this DE cancels with the other DE. The net electric field at the center of a ring equals 0. Okay, so for every charge, there is a charge on the opposite side that's going to cancel out the field. So up here would cancel with down here, here would cancel with here, here would cancel with here. So everything would cancel there at the center. We're going to come back to that one when we do the electric field due to a ring of charge. Now this one's kind of interesting. You could do the symmetry argument, or we could recognize that if we take our long positive rod and we shape it into a square, what we really have are 4 long positive rods. We've already covered what the electric field around a long positive rod would look like if our point P is a distance from the midpoint of that rod. So let's say we think about the top rod first. So this top rod is going to make an electric field that points away from that rod. So there's our first one. And then our next rod, let's say it's this vertical one, that's going to make an electric field which points away from the midpoint. And let's go to the bottom one. That's going to make an electric field that points away. And then let's go to the left one. That's going to make an electric field that points away. Oops, meant to use a different color there. So the electric field for this guy equals 0 at the center because, again, of the symmetry. The rod on the left makes a field that points to the right. The rod on the right makes a field that points to the left. Those guys cancel. The rod on the top makes a field that points down. The rod on the bottom makes a field that points up. So those guys cancel. So we have complete symmetry in this guy, and the net field is 0 at the middle here. This problem looks a little different. This time we take our long positive rod and we shape it into a half circle. We can still identify some symmetry. If we look at our half circle, the top half is a reflection of the bottom half, so it's symmetric about a horizontal line that goes through the middle. Let's draw that line. So there's our line of symmetry. We'll pick 2 points of DQ. So I'm going to pick one DQ that's right here. Doesn't really matter where I pick it. I'm going to draw DE. The really important part is where I pick the second DQ. So I'm a certain distance from the center with this DQ above the circle, or a certain angle. I can even label in that angle if I want. If I want to pick the symmetrically opposite value of DQ, it has to be the twin or the mirror image. So if this is an angle theta above, 30 degrees or whatever, then my other DQ should be 30 degrees below. So it's got to be symmetric. It's got to be the same point. So we would pick another DQ, which is the same distance below, angular distance below. We draw that DQ, or we draw that element of electric field, DE. What we see is that the y components of electric field, which would be the sum, in this case, since we have small elements of charge, the integral, that would give us 0. Our x components, this one is up and right, this one is down and right, so the up and down cancel, that's our y components. They both point right, so the net x component is non-zero. So then our net electric field would be the x component pointing in the x direction. Okay, hopefully that gives you a good overview of how we use symmetry to identify which components go to 0. Now, the good news is if you can't identify this symmetry, and truthfully sometimes it takes a little practice, if you can't identify it, the math will always back you up. If you didn't notice that your net electric field in the y would be 0, you would evaluate this integral and your answer would turn out to be 0. So the math will always have your back, but if you can see the symmetry, then you're just saving yourself some work.